Electronics in its various guises underpins modern society, from checking our emails first thing in the morning to glancing at the weather last thing at night. The average UK adult spends around 7.5 hours per day engaging with a desktop PC, laptop, tablet or mobile phone. Certainly, modern electronics underpins modern society and makes for a more efficient workplace. But how did we get here, and what advances in electronics have been made to get us here? Originally the size of a tennis ball, the transistor, a type of electronic switch, was invented in 1947 at Bell Laboratories in the USA. It has been adopted like no other technology before it. Estimates suggest around 3 sextillion transistors have been manufactured to date. That's a 3 followed by 21 zeros. That's more transistors than there are people on the planet. That's more transistors than there are cells in the human body. Indeed, that's more transistors than there are stars in the Milky Way galaxy. Every day, each of us carries around 2 billion transistors in our pockets. It is our demand and the societal appetite for ever more powerful electronics that has driven the multi-billion-dollar electronics industry this past 6 decades. It is the need for ever smaller transistors that has allowed for this increase in computing power. As the more transistors we can squeeze on a single chip, the more powerful the electronics can become. In 1970, a single transistor was around 8 microns in width, with around 1,000 or so transistors on a single integrated circuit. Today, a modern transistor is around 15 nanometers in width. That's more than 6,000 times smaller than the diameter of a human hair, and more than 500 times smaller than the diameter of a human red blood cell. There are around about 19 billion transistors in a single integrated chip in your home PC. It is this extreme miniaturization of modern electronics that is highlighting a number of the material failures in these materials. Indeed, it requires us to develop new kinds of materials that have unique and novel properties. Not only will this allow us to continue to miniaturize electronics, but it will also allow us to build new kinds of electronic systems and devices. From Harry Potter-esque e-paper that moves as you flex it, that is disposable and can be thrown away readily, cheap materials, but also new kinds of intercellular sensing systems and lab-on-chip to allow us to check our health and well-being rapidly and easily at home. A leader in the discovery and exploitation of new nanomaterials, the UK finds itself as a leader and at the forefront of international nanoscience and nanotechnology research. Here at the University of Bath, we are using the cutting-edge facilities to grow, atom by atom, new kinds of nanomaterials that are not otherwise found in nature. From truly two-dimensional materials such as graphene, a honeycomb of carbon atoms that is a single carbon atom thick, essentially a single plane of graphite, to the growth of carbon nanotubes, rolled pieces of graphene that form concentric tube-like structures. It's through the use of these new kinds of nanomaterials, not found in nature, that we can build new kinds of electronics. From smart plasters that can communicate your health to professionals, to new kinds of intercellular sensing platforms that can probe the internal environment of cells. We can produce new kinds of flexible displays and new kinds of electronics that otherwise could not be built. Nanotechnology is set to lay the foundations for the next generation of electronics. In the electronics we'll see in new kinds of biocompatible, flexible, truly transparent electronics.